Hi, my name's Brett Moore. I'm currently a junior at East Carolina University. A little bit more about my background. I study in information and computer technology with a concentration in computer networking. I currently study a little bit in cybersecurity and network security as well, and I'm currently pursuing my CCNA security. I have already achieved my CCNA route and switch for Cisco. And today we're going to talk about the Spectre and Meltdown attacks, the two architectural issues that changed modern processors. These two attacks or these three attacks are actually on such a wide scale that that many companies are scrambling to get this caught up and patched before hackers take advantage of the obvious threats that are now out there. But I would say that before we get started, that most of the attacks are sophisticated and are actually in just a proof of concept, which we'll talk about a little bit later. So, what is Spectre and Meltdown? As I mentioned before, this is just the name of a trio of high-risk vulnerabilities that has now affected almost every Intel processor, along with some AMD and some micro ARM processors. These flaws derive from core architectural features implemented into modern processors that help them run faster. All three variants involve malicious programs gaining access to the data that normally users wouldn't be able to see, such as kernel memory and kernel virtual memory. Two important features of the modern processors that are exploited are called speculative execution and caching, and side channel caching, which we'll talk about a little bit in a few minutes. So let's talk about the Spectre attack. As I mentioned before, there are three vulnerabilities in play here. However, two of them are dubbed the Spectre attack, while one of them is the Meltdown attack. The Spectre attack is most notable because it uses speculative execution to trick programs into revealing some of its own data. So what this basically means is that a processor uses this feature called speculative execution, which kind of predicts how data is going to travel or how it's going to be checked by the processor, and it can make calls before things are returned, so that the processor knows that execution was properly executed. So it does this by utilizing two methods of an attack called bounds check bypass and branch target injections. You can actually find a little bit more information if you just do a quick Google search for Spectre and Meltdown. And at the end of my sources as well, I have these two PDFs that actually are outlined by the company that founded these attacks. And they'll give you a little bit more information about the bounds check bypass and branch target injection. It's highly, highly technical. The Spectre attack tricks the processor into speculatively executing instruction sequences that should not be executed during a normal process. Therefore, you're able to kind of trick the processor into doing something that it wouldn't normally do, and by doing this, you're able to bypass bounds checks, which allows you to return memory values. And if you are able to return the memory values, you can check the contents of those memory values, and therefore you can figure out what's being hidden in there. And you can even get a little bit more detailed in each attack and actually specifically have the processor return specific values that you're looking for. As I mentioned in the beginning, these attacks are in proof of concept. So right now there is no 100% foolproof way to exploit this. It's kind of a case-by-case basis. But some of the methods of execution are using JavaScript, conditional branch exploitations, and there's other methods that can be found in the sources as well. This attack requires a very intimate knowledge of how processors and software works. Without that information, this attack is pretty much not able to be done by the average person. So commonly, you'll see the Spectre image reference with this image that someone just mocked up, kind of similar to the Snapchat ghost, actually. So let's talk a little bit more about Meltdown. So Meltdown is actually confined to almost specifically a few set of Intel chips. An attacker is able to access the machine and see data from the machine that would not normally be able to, normally a user would not be able to see. This falls kind of in line with Spectre, where each method is slightly different, but the attack is actually different, but the return is pretty much the same. The only downside or the upside is that an attacker would not need to know an intimate knowledge of how the processor and how the machine works. This attack is a little bit scarier because anybody can seemingly perform this attack if they were to gain access to a host machine. The Meltdown attack allows for overcoming of memory isolation by allowing the user process to access and read the kernel memory. And the reason why the kernel memory is so sensitive is that let's say, for instance, you're working with multiple programs. Well, these programs store sensitive data in kernel memory. There's actually processes in the processor that isolate these tables from one another. And essentially, Meltdown works by gaining access to these tables by allowing a person to write data from a administratively privileged program into something that doesn't have the rights to read that. And when it does this, it allows you to retrieve information that's highly sensitive to other programs, such as passwords and usernames and hashes and other things like encryption keys. Very, very sensitive information that you would not want someone to see. And this is done using a function or a processor function called out of order execution. And this allows the attacker to cause a kernel dump, and that kernel dump dumps its memory and mapped memory addresses, revealing the highly sensitive information we discussed. And like I mentioned before, this is the common diagram or the common image you would see with a Meltdown attack. So if you ever see this image, it's possible that someone is discussing the Meltdown attack or possibly writing a new proof of concept for Meltdown attacks. The source here, you can actually find a PDF that talks a little bit more about how the Meltdown attack works in very, very detailed description down to how the processor functions and how the out-of-order execution is actually caused inside the processor. And one of the most notable things about this attack is that it exploits functions that were designed to increase performance on processors. So many modern-day processors are affected because most modern-day processors allow these functions to occur so that users can see an increase in performance over older processors. So here we're just kind of listing the differences between both attacks. As I said before, the Spectre attack requires a very detailed and intimate knowledge of processor architecture and execution, while the Meltdown attack is complicated. It's not as sophisticated in its approach, and it does not require such an intimate knowledge of how the processor function works. Speculative execution is used to trick the processor into revealing information in the Spectre attack, whereas the Meltdown attack uses out-of-order execution and side-channel caching to reveal data in the kernel. Spectre is dangerous because it affects almost every modern-day processor in the last 20 years, but Meltdown, while it is something that you would want to patch first, it only affects specified Intel chipsets. Those Intel chipsets can actually be found in my sources at the end if you wanted to take a look and see if you're affected and how you might go about patching. So, speaking of which, how might you protect yourself from these attacks? This slide shows some of the release dates of the software patches and the microcode patches that different companies released for some of the most used products on the market. So Microsoft released a patch for processors supporting Windows 7 and onward on January 11th. Apple released its patches for Mac OS, iOS, and the TV OS on January 3rd. Google published a list of affected devices and how to fix them near the start of the year. And Firefox and Google Chrome both released beta patches for their respective products in January 23rd. So before I talked about how these attacks utilize exploits that deal with the functions that that have led to performance increases in processors over the past 20 years. However, the new fixes for them actually cause most processors to even further isolate the kernel memory from other processes, so that even if you were to try to perform some sort of privilege escalation, the processor or the kernel actually isolates itself even further with more boundary checks in place. However, this causes a pretty massive hit on performance because it essentially disables some of the program or functions that were used previously. Phoronix is a company that studies a little bit more about how much of the performance hit is actually measured, and they're measuring about 5 to 10% across the board for Intel processors. However, some companies have reported in some of their data servers or data centers using higher level Intel chip processors that the performance hit is up to 30%. And here are my sources. Thank you.